Thank you very much. Thank you very much, Katja, and thank you very much for the invitation. Okay, let me go to the plan for the talk. The so-called interior problem for the plane radon transform is known to be not to be injective. But the well-known example showing this fact is rotational symmetric. So for some time, I've been aware of the fact that one would like to have more general examples which are not rotational symmetric to sort of complete the picture concerning the impossibility of the non-injectivity of the interior problem. But that was not so easy to construct so examples, but a couple of years ago, I got an idea that I was very happy with. I was sure that would solve the problem, namely to construct a distribution, a compactly supported distribution whose radon transform is supported on the set of tangents to a bounded convex domain. But that didn't work. And finally, I was able to prove that this is impossible unless the domain is an ellipsoid. So I will show you such examples in the case of a circle and explain more exactly what I wanted to do. And it turned out that this question is related to a famous problem of Arnold. I will explain this, and then I will say a couple of words on the proof of the main theorem. And then I will talk a little about some local questions that are related to this, which are one result that is fairly recent and some open questions. So let me say also that I talked about this when the first result of this type was new. I gave a talk on this in Malta in 2018, and that's where I learned for the first time about Arnold's problem. And since then I've talked about this a couple of times, so some people present may have heard part of this talk. I hope this is some repetition is okay. But anyway, it's not the same talk because the project has evolved over the time, because since then I've written 4 papers on the problem. So, okay, my notation is pretty standard, so I think I can go quickly over this. I sometimes prefer to use geometric notation, and thinking, it means that the radon transform is a function or distribution on the manifold of lines or hyperplanes, perhaps. But sometimes we need, of course, the identification of the hyperplanes with a pair omega p like that, so that the radon transform becomes a function of a set of such pairs. It's even, of course. And we need also the adjoint transform to define distributions, but this is well known, was done by Helgason and Gelfand School 50 years ago. So here on this page, the bracket means action of distributions on test functions. So this is how radon transform of a distribution compact. I will only talk about compactly supported distributions. And we associate locally integrable functions T omega p with distributions by this definition. Now, what has the interior problem to do with this? Let's recall what we know, for instance, what is written in Natterer's book in the 80s. When we consider radial functions, the problem becomes one variable problem. So by an integral equation, it's easy to find functions, radial functions, which have the property that the Radon transform is zero on all lines that intersect the smaller disk, but the function is supported in the bigger disk. Now, suppose we replace the disk by arbitrary convex sets. And this, the corresponding statement seems not to be known. I think I would like then to construct an example, similar example, which means that the function should be supported in the bigger domain, but the Radon transform should vanish over on all lines intersecting the smaller. This is, I'm talking about the plane case, two-dimensional case. But the same problem we have, of course, for all even dimensions, but the conjecture is obviously not true in odd dimensions, because then the inversion formula is local, as we know. So here, so here was my proof idea in order to reduce the problem to a one-dimensional problem, as we did a minute ago with an other question. So I wanted to find a distribution supported inside the blue curve, whose Radon transform is supported on a set of tangents. So that was the reason for asking this question, and it didn't work, as I said. Now, to make all this more concrete, so to speak, I want to show you an example in the case of a circle, where one can find such examples. And it's very easy. Begin with this function f0, which is integrable over the plane, supported in the disk, closed disk, and it's even integrable along all lines. And an easy computation shows that the Radon transform is 1 for all functions for all lines that meet the open disk, in other words, for absolute value less than 1. So then we can cook up a distribution by taking the cluster operator in the distribution sense of this function, and to compute the Radon transform, we use, of course, this familiar relationship here, which is valid for distributions also, of course. So we have to take the second derivative of a piecewise constant function like that. And the result is, of course, delta prime, like that. P equal to plus minus 1 corresponds to tangents. So this is what was not possible in general. This is of no interest for us, but as a curiosity, I show you the function, the distribution, the restriction of the distribution to the open disk is a function like that, but of course, wildly non-integrable near the boundary. So for ellipses, one can do the same. And here was a question that this led to, and the theorem. And I wrote 2 papers because it was much easier when the domain is symmetric with respect to a point, reflection symmetric with respect to a point. So I wrote the first paper on that and the second on the general case. Of course, yeah, I don't need to assume that the boundary is smooth in the theorem. So just a couple of words. I think many people here know about the connection of this with Arnold's problem, but for complete, let me say a couple of words. If this question goes actually back to a famous lemma of Newton, but I don't have time to explain this. It's a very interesting story. Anyway, if we compute the volume of on one side of a hyperplane through a ball, now we are in 3 dimensions, then it turns out that the volume depends polynomially on the position of that plane. And the same in all odd dimensions, because that square root will be raised to an even power. But it turns out that in even dimensions, the volume function is not even algebraic. So this was a reason that Newton posed a question, or rather wrote this famous lemma that I mentioned. And Arnold's problem asks if are these the only cases when the volume function is not algebraic even. So there are 2 things to prove, one can say. The first that was done by Vasiliev as soon as 1 year later. So if n is even, the volume function is never algebraic. So remains the odd case, and it's still unsolved. But people tried to answer an easier question by assuming more, that the function is not only algebraic but polynomial. So there were for a while several papers on this. Special cases were settled, and finally the question was definitely settled by an article by these 3 people. And now the interesting fact, amusing fact, is that my theorem implies this. It's rather obvious as written there, because that the volume function is polynomial for fixed omega means that the Radon transform of the characteristic function is a polynomial of P in the interval, relevant interval. So we need only use a formula that I used before and apply Laplace operator sufficiently many times so that this polynomial, the P derivatives of that polynomial become 0. So we get a distribution which must be supported in the set of tangent planes. Notice now the dimension is arbitrary. Yeah. So that's it. Now, next, we'll try to say a couple of words about the proof. So what the strategy is easy to explain of the theorem. Yeah. The first is to write down an expression for an arbitrary distribution of G of omega and P on the manifold of lines that is supported on the set of tangents to the boundary. And then we have to adjust what can be varied in this expression so that that distribution is in the range of the Radon transform on compact interval. So and these are well-known range conditions, so that all these moments with respect to P have to be homogeneous polynomial in the components of omega of degree k for every k. And then the final and main step is to prove that in this way we get infinitely many equations. And we have to prove that these conditions imply that the boundary curve is an ellipse. So if the distribution is of order 0, the proof is a couple of lines. It's amazingly simple. Let me do it. We need to introduce, to write down such an arbitrary expression. Expression for an arbitrary distribution supported in the correct way. We need, of course, a supporting function for the domain, which is defined like that. And now, clearly, a line, L omega P, is tangent to the boundary if P equal to rho omega, and on the other side, if P has the value which is the infimum of that instead, which is the same as that. And since we have assumed here for simplicity that D is symmetric like that, rho minus omega is the same as rho omega. So a distribution of order 0 satisfying this support condition must be of this form, where the only, apart from rho, which is assumed given, the only unknown object is that density function Q, which a priori might be a distribution, but easy to see must be a function. So we have to use the range conditions. We need, in this case, just two conditions. If K is 0, the range condition means that this integral has to be constant, a polynomial of degree 0, that is constant. So Q must be constant. And because of the evenness, symmetry condition, I made all odd moments are 0. So the next interesting moment is the second moment. And then we see that simple computation that rho omega squared must be a homogeneous polynomial degree 2. And it's an easy exercise to check that the supporting function is a, I forgot to say that the supporting function is by definition homogeneous of degree 1, positively. So we know already that rho omega squared is homogeneous of degree 2. So we only need to know that it's polynomial. It must be a quadratic polynomial. So this is equivalent, since it's bounded. It must be an ellipsoid. So that is surprisingly easy. So let's go to the case what is the time? Okay, I need to speak more quickly. So there's some interesting matrix identities I would like to show you, which you can see a little of already in the case of first order, first degree distribution. Then an arbitrary G distribution of order 1 supported in the way we want must have this form where Q0 and Q1 are arbitrary densities. And the minus sign is needed because we must have G even. And we have to make computations of this form, many. And so the range conditions look like this. We go to, this is repeated on the next page. Here, you will see for a while equations like this, several. Let me just repeat. Here, everything depends on omega. And rho, everything is unknown in some sense, except that we know that pk is a homogeneous polynomial in omega and omega 2 of degree k. And what we are interested in is the rho, of course. We have to prove that rho square is a polynomial. So since we have many equations, we can, of course, eliminate the q's and immediately deduce that rho square is a rational function, actually, yes. And then I can already at this stage say the crucial point, namely, if we can show that we can show in infinitely many ways that some power of rho square is a rational function using different pairs of these infinitely many equations. But the crucial fact would be that the degree of Q is bounded with M. This shows that this rational function must be polynomial. So let me just, since actually this, I believe that this matrix calculus that appears here has some independent interest, but it must be known. I'll come back to this, but I have not found anybody who have seen it before. And also I will show at the end of the talk that it can be used to prove something apparently completely different. So therefore, I want to spend a couple of minutes to show you a little of this matrix algebra. What I will do is to use this infinite, I will translate this to infinitely many equations like this, where by picking out the successively the square submatrices of that big matrix. And I call them M0, M1, M2, etc. So this is M1, the upper square, M1 is the next, and so on. Now, I want to write this even shorter by giving a name, capital Q, to this vector of densities, and P0 is the vector of the first two polynomials, P1, the vector of the second two, and so on. Then I have sequence of equations. Did I write it on this? Yeah, like that. Lower, like that. And now what is crucial is that this sequence of matrices turn out to be a geometric series in the sense that there is a matrix which is a factor like that. And that makes it possible, yeah, similar like that, makes it possible to, here I've just written out the first two of those equations. S P0 equal to P1 and the next. And now I've combined those two matrix equations by just writing the column vectors beside each other. And now I can take determinant, use the product law for determinant to, since determinant here is rho square minus rho square, I get already that rho square is a rational function, which I already knew, but now it's very easy to take the next step that I indicated. In the same way, these equations that I showed you show that I can do this same trick for a higher k. And then I get exactly what I mentioned earlier, namely that an arbitrary power of rho square is a rational function with the same denominator. Hence, it must be a polynomial. Now, what is nice is that this can be, I need not spend much time of this because now you hopefully know what's going on. I do this, I consider for m equal to 3, for instance, a sequence of square submatrices, which I call M0 and M1. And I do play exactly the same game. There's one new feature now since the matrices are bigger, namely when the matrix S, where is it? So let's see. Yeah, here you see matrix S. On the trivial, there must be one sequence of ones here because it's a translation going on. And the last row it's obvious, must contain powers with certain coefficients there. But it's not completely trivial to compute the determinant of S. But the quotient on the other side, the right quotient, helps us to do that because the T, remember what T is the quotient from the other side, so to speak, has this simple form, it's almost diagonal. So determinant must be the same. So therefore, yeah, that's all I'm going to say about this case. So this is essentially the proof in the symmetric case. I don't think I've forgotten anything. No. Now, I won't bother you with this. There is I think, a cute feature of this matrix algebra here in the non-symmetric case. In the non-symmetric case, everything, the M and the Q have to depend on two variables, namely because the expression for an arbitrary G, which is correctly supported, must contain a term with rho at minus omega also. And the same with the densities in front. Now, when we discuss the matrix algebra, we can forget about the meaning of rho and rho check, which is as a short form. And so, but what is, I will only show you a couple of things about this matrix business. Namely, that the important fact that this fact that written here, that the MKs form a geometric series in this case, with quotient from left and above, I call S and T, and the T has a simple form because it's a block matrix where the determinant of each is very easy to compute. And the S, earlier the coefficients here on the last row in S were powers of row of all orders, various orders. But now we have two variables, so instead they are, it's written here, they are actually elementary symmetric polynomials of various orders in 6 variables evaluated at this point. So for instance, like this. So this is the structure of S. And so knowing this, we can use the same argument, and the result will be, well, we shall very easily see that some power of this product is a rational function. And using the argument shown earlier, we end up with showing that this rho omega rho minus omega is a polynomial, hence quadratic. And now, when I wrote my second paper on this, unfortunately, I failed to understand that this object is better to deal with than rho square. I was sort of stuck with the idea I had to prove that rho square is a polynomial. But this was unfortunate because this has better properties. For instance, it is, as soon as we have dropped the hypothesis that D is symmetric with respect to some point, we don't have any preferred point to put in the origin at all. So it's very good to have an expression which is translation invariant, whereas this is not translation invariant. So that was unfortunate. So that proof has to be simplified. So how much time do I have? Yeah, maybe I can manage. Oh, well, I should ask, are there any questions so far? Because now I'm going to talk about different questions, but the point is that at least in one case, the proof depends on essentially the same arguments. So if there is a question on this or something unclear, okay. Yeah, the first local question is, it's actually better to see a figure than read 5 lines of text. My first local question is simply the same question, but local. That is, D is now, we are only interested in small portion near the boundary of the domain. So domain can be unbounded even. And we are considering only an small open set of lines near that tangent. So, and the assumption is that the integral is 0, or always. That is, but that would, yeah, yeah, of course, I forgot myself. It must be a distribution. supported inside DR. And the restriction of the Radon transform to that open set of lines is supported on a small portion of on the set of tangents near that. So that's the question. And in general, we don't know. I've proved some special cases, so I'm beginning to believe it is true. And if it is true, it has to be proved by completely different methods. But maybe I will return to that. But without assumption on like that, it's not true. And this simple example shows this. You see, it's a product of delta prime of x1 and unit characteristic function unit into as function x2. So it's a function supported on that line segment. And clearly integrate over any line which intersects the interior of the interval transversely will be 0. So this has this property. But I would like to add that this is connected with a well-known and important examples of Helgason. You know, he needed to complement his famous support theorem, where the assumption is that the functions decay at infinity more rapidly than any negative power of absolute value x. To complement that with examples showing that this assumption was needed. And for this, he has, for instance, in 2 dimensions, homogeneous functions that are homogeneous of degree -2 and mean 0 over circles. And if I cook up a function, say a continuous function inside this angle by adding rotated versions of this distribution around that point, then I get such example. So this is related to that. Anyway, so that was the first local question. Now comes to a even more interesting local question. I hope I have some time left. Yeah. On my screen, I can't read the title. Can you? There is some, doesn't matter. So the question has to do with relationship between singularities of a distribution at boundary points of the support and geometry, perhaps singularities of the boundary curve or something like that. It has to do with that. And an obvious example, very important result of this kind, is Hermander's famous proof of Holmgren's uniqueness theorem for PDs with analytic coefficients. This was done, the same thing was done independently by these 3, roughly simultaneously by the 3 people. What does the theorem say? Well, the proof of the Holmgren theorem consists of 2 parts. That's the beauty of it, that are completely independent and very interesting each. And one part, which I don't talk about here, is a microlocal regularity in terms of analytic wave transit for PDs with analytic coefficients. And the other part is this. It says that if C0 is an outer normal at the boundary point of the support of a distribution, then both these elements must be in the analytic wavefront set of F. And what is an outer normal? Well, it's rather suggestive from the figure. For instance, C is an outer normal at x0 if there is a hyperplane that is conormal to C and is also a supporting plane to the support at the point. But more generally, an outer conormal, C is an outer conormal if there exists a choice of real analytic coordinate system near the point that makes a situation like that. That's an easy way to say it. So this is now the other examples given here, facts given here are not really related to my problem, but well, in some sense it is. Actually, using this very interesting concept, wavefront and wavefront set, one could immediately ask lots of questions. For instance, if F is a characteristic function of that K here, what is the wavefront set at the point? In this case, one can directly from the definition compute the wavefront and analytic wavefront set. It must contain all C's above that point. And actually, using more sophisticated methods, it was proved by people like those mentioned there that even if we only know that the support is contained in K and that point is in the support, all C above that point must be, and so on. And something, the same is actually true with much weaker singularity of the boundary than being a corner point, namely just discontinuity of the second derivative like that. I mean, these things require, but depend, the proofs depend on theory of plurisubharmonic functions, rather sophisticated and perhaps more as well. Anyway, so I gave this, showed this to tell you that there has been some interest in discussing, proving theorems of relationships between singularities of the distribution and the boundary. And my second theorem, which I will show you now, I can't read because, I hope I have some, I'm not talking too much about that. Now I will consider for a while only distributions supported in hypersurface, just as in the first part of the talk. My Radon transforms were supported in hypersurfaces. So I will show you first the easy facts, which are sort of go in one direction. If we have a smooth piece of a smooth, all my results are local, smooth piece of a hypersurface and smooth density, then the only possible wavefronts are the conormals to the surface. And the same for analytic wavefront sets. And the same for higher order distributions. if the distribution is order M, we need M density functions. And if everything is analytic, the same statement about the analytic wavefront set. Now I'm interested in rather strong converse to this statement. That is, I want to assume some microlocal regularity of the distribution F at the point. And I want to conclude that the surface and the densities are analytic. And what makes me, again, what I think is interesting at this can be proved with essentially the same argument as I showed you earlier. So here is the theorem. First version of the theorem. I will show you also a coordinate-free. Oh, well, it's time. My time is out almost.
Please take your time. Please take more time.
Okay. So say we have a C1 surface and continuous densities, and especially like the one on the previous slide page. And now we want to assume a rather weak regularity assumption concerning, of course, other cotangent directions and then the conormal. And in 2 dimensions, we need just one xi and opposite. In this case, you see, if the x's are horizontal, they are not conormal. And if these are not in the analytic wavefront set, the conclusion is that for every line, well, I wrote here, but okay. The conclusion is that surface must be really analytic and all densities also, but it's, of course. Well, I think we skip that. I wanted to show you that it took me a while to see that, but after a while I saw that there is a coordinate-free formulation. So then we are in a real analytic manifold and a piece of a hypersurface and a tangent vector that is transversal, then and all conormals to at the point to that we have to assume are not in the analytic wavefront set. And again, in 2 dimensions, it's just one vector and its opposite. Then the conclusion is, as I said. So now it remains for me only to try to explain how can it be that so completely apparently unrelated theorems are proved with almost the same arguments. Well, I will try to make that plausible. And that's my last page, I think. Look first, I'm going to look at the assumption and conclusion of first theorem 2. The assumption is a microlocal regularity property of the distribution. And the conclusion is that the supporting hypersurface is real analytic and more. Now, how about, is there a similar structure of my first theorem? Then, of course, the Radon transform, G, plays the role of F. And it is also supported on a hypersurface, as I said. And the assumption that we used was that all these moments are polynomial. And already if they are real analytic in omega, this means that the conormals of the p-axis is disjoint from the analytic wavefront set of G. And in this context, I couldn't help the temptation to show you here a tomogram. What's it called? They call it a sinogram. This is the Radon picture of the Radon transform of the Shep-Logan phantom. And you'll see that there are no vertical contours, vertical discontinuities, and can never be. And this is because of that. And that is well known, of course. And now, how about the conclusion? The conclusion, if there is an analogy, the conclusion should be a regularity property of the supporting hypersurface. And indeed it was. It says that as strong as it could be, except being plane. It's a secondary, it's a ellipsoid. So that's the similarity. No, my time is up. That's essentially the talk. But concerning, I have one word concerning this matrix. You see, here's a little list of, and the last item here on my list is not a publication. I wrote down a 5-page set of notes a couple of years ago on this matrix identities, and showed a number of people without, because they must be known, and they are elementary, of course, but they are apparently fairly powerful. So I'm asking this audience here if I forgot, but I'm planning to put this set of notes on at that address tonight. So you're welcome to look and see if you recognize this or know some other application. So that's all. Okay.
Thank you very much. Thank you very much, Jan, for the very, very nice talk. Thank you very much. Are there any questions or comments, please? Please feel free to unmute yourself. Are there any questions or comments, please?
Everything was completely clear.
Are there any questions or comments, please? Can I ask a very, very small question? I mean, you explained the idea of the proof of your theorem in dimension 2. Could you please say a few words about higher dimensions?
Oh, it's the same.
I see.
Yes. Yes. Why did I do that? Probably because notation was simply. Yes, it's exactly the same. There's no difference. No.
I see. Thank you very much. Thank you. Are there any other questions or comments, please?
So, Katya, I have a question. This is Venki.
Please.
Yeah, hi, and I have a...
Is this Venki?
Yes.
Yes, very good, very good.
So I have a question. What if you, in higher dimensions, replace hyperplanes by lines?
In the first, you mean in the first part of the talk?
Yes.
Well, then, for instance, well, to begin with, the corresponding transform is overdetermined. You know, we have already the set of lines in free space is 4-dimensional. Maybe one could ask similar questions. Funny, I didn't think of that. Then maybe one reason I didn't think of that is that the relationship with the Arnold problem appears to be lost. Oh, I never thought of it.
Okay, yeah, thanks.
Thank you very much. Are there any other questions or comments, please? If not, thank you very much, Jan, for the very, very nice talk. Thank you very much, everyone, for coming. Thank you very much.
Thank you very much. Thank you.